Hey everybody, Bill Sky, the Assembly Guy, and what we're going to do in this video is we're going to talk about this thing called table-driven selection. Now, if any of you, and most of you should, but if any of you have seen the switch statement in C, C++, Java, I mean they're everywhere. The switch statement is basically a group of if statements without an if statement that interrogates an integer. So switch statements are absolutely wonderful for menu-driven programs. They're good for checking the status of maybe a Boolean. Anything that requires more than just one if statement and you're dealing with the same amount of data and it's basically simple comparison to a value you're looking for, switch statements are actually very, very useful. And they've been around for years, but they're still a great logical construct that can really help you, especially as I said earlier with menu-driven programs. So I'm going to do a video on x86-64 switch statements as well as ARM, and this is the same introduction for both. I suggest you watch both, but I've got both the x86 and 64 ARM in separate videos. So let's get going with table-driven selection. Okay, so I have an assembler program up here, but just to remind you what a switch statement does. A switch statement, you simply use the word switch, and then you, in parentheses, you specify some variable. I'm going to do this as if it's C++ or C. So I'm going to say char menu selection equals 3. Now, the thing that you're interrogating in a switch statement must be an integer. So what I'm going to do here, now a char is an integer, so that's okay. So I'm going to say switch menu selection. And then within the switch statement, you have a bunch of case statements. So you specify case 1. I'm going to call a function. I'm not going to say call, I'm just going to say function 1. And then you say break. Case 2, you call a function. I'm going to call function 2 here, and then I'm going to break. And then you normally have a default, which means that if it wasn't 1 or 2, if it was something else, I'm going to call a function 3 in this case, and then I'm going to break. And then that's the end of my switch statement. Now, many of you may have learned that it's always a good idea to put this group of statements underneath each case into an open and close curly bracket. I do it that way. It doesn't make the program any larger, but I've seen compilers where if you don't put all those statements in curly brackets, you might have an issue. So anyway, so that is the basis of a switch statement. And basically it's a bunch of if statements. Now for two cases, it's not that big of a deal. You could easily do a bunch of if statements or two if statements. But if you've got a switch statement, or if you've got a value that you're checking like 50 different values, it can be a real problem to have multiple if statements. So switch statements are very useful, and that's a quick little overview of the switch statement. Now let's get on to the assembler implementation. Okay, so this is x86-64, and what we're going to do here is we're going to go ahead and create what we call a case table. Now a case table is an array of data, or just a group of data that's almost like structures, and let's just start doing it. So I'm going to call this case table. Now you might want to call it something more interesting than that, but I'm going to call it case table. And what you do is you define a byte and the value that you're looking for, in this case the value 1. So we're looking for the ASCII value 1. And this is because the user has typed in a menu option. So I'm going to pretend here that we have a menu that the user is going to be going through. And one of the options is 1. Then what you do is, and this is a 64-bit project, so I'm going to define quad. Then you specify the function name that should happen if the user selected option 1. Then you select option 2. You specify the function name for option 2. You specify option 3. That's going to be function 3. You specify option 4 in this case. And you specify the function that's to run there. Now, you might wonder, why are we doing a byte here and why are we doing a quad here? Is because the byte is the value we're searching. It's the value that we're looking to match. And that's almost always how you do it. Now you could do it with a word, a double word, or even a quad word there, but in this case it's just a single character that the user typed in on the keyboard on a menu option. So that's why we did that. And then why did we do a quad here for a function? Well, this is really different. What you're doing here is when you're saying define quad function 1, what you're doing is you're saying put in this memory location right here, right below the 1, put in the address of function 1. And for 64-bit applications, that address is always 8 bytes. 8 bits times 8 bytes equals 64 bits. Now, if you put define double in here, which would be for 32 bits, 8 times 4 is 32, 8 bits times 4 bytes equals 32, you're going to get an error in your 64-bit program. However, if this is a 32-bit application, you want to make it define double. So that's definitely how you do it. But in this case, since it's a 64-bit, you specify that. Now, normally there's like a default, we'll get into switch, we'll get into that in the code, but you basically are specifying what should the program do if the user types in 1, go to function 1. Now, those functions are not defined. If I go up here and if I save and then build this, I'm going to get a number of errors. It doesn't know what function 1 is, function 2, and function 3. So it wasn't able to put those addresses into that memory location. So what we're going to do is we're going to come down here and we're going to say function 1. I always like to put a no op and then a return. And let's make sure, did I capitalize those? I certainly did. All right. So let's go ahead and copy those 3 times. And just change the function name to 2, 3, 4. Now I hope when you write your code on a menu, especially it's a menu, you want to do those functions names where they mean something. You don't want to make it as cryptic as function 1, function 2. Like for instance, if option number 1 in a menu might be open a file, you might want to say open file function, something like that. But in this case, we're just doing it just to demonstrate the concept. All right, so let's save and build this. All right, great. It worked out great. So we've got the data structure of the case table, but there's some constants that we have to create. Now, by the way, this is exactly the same on Linux and Windows. There's absolutely no different. ARM, it's a lot the same on ARM too, but that's in a different video. So there's a couple of things that we need. We need to know how big these two values are together. So a byte is 1 and a quad is 8. So you could hard code that into your code, or you could create a constant, and I'm going to call this .entry size equals $ minus case table. And what that means is that the case table .entry size constant is going to contain the number 9, which is going to be the quad of 8 and then the byte of 1. 8 plus 1 is 9. Now, the nice thing about this is that if you were to just simply copy this over a 32-bit program, this would still work. You would want to change the quads to doubles, but your constants would still work. So that's very useful. And why do we need to use those constants? Because we need to be able to go from the 1 function 1 entry to the 2 function 2 entry to the 3 function 3 entry. So we need to add 9 bytes to the address every time we're doing this in the actual code where we're implementing the switch. So you'll see that as we move on. The other thing that we need to know is we need to know how many entries are in the case table. So we have 4 entries: 1, function 1, 2, function 2, 3, function 3, 4, function 4. So I'm just going to say number of entries equal, and I could actually say 4, but what happens if you decide to add a number or a menu option to your menu? Okay, what if I decide to add define byte X for exit, and I say I'm going to run an exit function to do that? Well, now I've got to come down here and change this. And that might not be a big deal, but it is when you're having to give your program to somebody else or somebody else is looking at your code and figuring out how it works. So instead of doing that, I'm going to say the current address minus the address of case table. So that's going to give us the total number of bytes allocated here between here and here. And then I'm going to divide that by the case table.entry size. and that's this one right here. So that's going to divide those, I don't know, what is that? That's 9 times 5 is 45. It's going to divide that by 9 bytes, so 45 divided by 9 is going to be 5 entries. And that's it. That's your case table. Now, one thing that I didn't do here, I didn't create the exit function. So I'm going to come down here to the bottom, and I'm going to create the exit function and just say no op and then return. And then it should go ahead and work. So let's go ahead and build this. And it looked like it built okay. All right. So we've got the data structure in there. We've got the functions that should be executed each time, you know, a 1 is found or a 2 is found. But what is the actual code to do this? Now, one reason why we use case tables or table-driven decision making is because we don't want to have our code filled with compare and jump statements. It just spaghetti code crazy, right? We don't want to just have all of those things in there. So what we're going to do is we're going to create a little loop here. And I'm just going to create the loop. I'm going to say, I call it case loop in this case. And then I always put one down here called end case loop. Okay. So now let's get started with this. So there's our, we haven't actually got the loop, but we've got the labels there. So what I'm going to move, I have to move into some register. In this case, I'm going to move it into EBX. I could move it into RBX. Let's move it into RBX. I'm going to move in, because this is a 64-bit application, I'm going to move into RBX the address of the case table. So RBX now has the address of the case table. It might actually be better to put this into RSI because it's an index register and it's really meant for addresses. Okay, so I'm going to move the address of case table into RSI, and I'm going to move into RCX. Oh, I forgot my commas. I'm going to move into RCX the number of entries in the case table. So I'm going to say case table dot number of entries. And that's going to be the number of entries in the case table. Now, why do we need these two things? Well, because our loop is going to be analyzing each entry in the case table. That's why we need the address of the case table into RSI, and we need to know how many entries are there that we're going to be interrogating. How many things are we going to be analyzing in the case table? So we put that in the RCX register because that is the register that we use for loops. Okay, so we're pretty much there. So what I'm going to do is I'm going to put a test value. I'm going to move into AL the number 1. Okay, that's my seed value. That is just a seed value, testing value we are searching for. Now, normally what you would do is you would actually have the user type something in, and you would just interrogate what they typed in. And we might be able to get to that in this video, but let's see how far we get. Okay, so we have a value into AL. So what I'm going to do is I'm going to compare AL with the value that RSI is pointing to. Now, what does that mean? Well, RSI is pointing to the address of case table, and if we come up here to case table, what are we comparing AL with? We're comparing it to the address, the data at the address of case table, which is the letter or the ASCII value for 1, which I believe is 31 hexadecimal. So it's going to be looking for that. Okay, so it's going to compare that. Then I'm going to say jump if not equal. Now I could say jump if equal, but I'm going to have more jumps and more labels. I'm going to say jump if not equal to, I don't know, next case loop. That's just something. And let's put a comment here. Compare our value in the case table with AL. If not the same, go to the next value in the case table. Okay, so that's what our comments are saying to do, so let's do that. So I'm going to say next case loop. So how do we move to the next value in the case table? So right now RSI is pointing to this. How do we move to this so we can now check to see if it was the number 2? Well, we have to take the total number of bytes in this memory location, and we have to add it to RSI because RSI is pointing to case table, and that'll take us to there. How can we do that? Entry size. That's why we created that constant there. So I'm going to simply say, to go to the next one, I'm going to say add to RSI case table dot entry size. point RSI to the next value in the case table. Let's make sure I got that right. Entry capital S-I-Z-E. Okay, good. So we go ahead and do that. And then what we're going to do is we're going to say loop the case loop. So that's going to take us back up here to check to see if the number 2 is what the user typed in. All right? So, boy, we're almost there. All right. Now, if it is equal, what do we want to do? So if it's not equal, that means it is equal to the number 1, which in this case it is on the first one. What do we want to do? Well, we could print out some stupid statement. Well, I shouldn't say stupid. We could print out something and make our case loop very, very complicated. But instead, what I'm going to do is I'm going to call the value in RSI plus 1. So I'm actually going to call that as a function. So let's take a look at that. Right now we're pointing to the 1 in our case table. And I want to call this function. How do we do that? We add 1 to the address of RSI because RSI is pointing to the case table. And because why 1? Because a byte is 1. And that's going to point us to this memory location, which is the address of function 1. So we're going to call the function. It is the same. So call the function pointed to in the case table. All right, great. And then when we're done with that, we're going to say jump to end case loop. Then leave the loop. Pretty neat. Let's go ahead and build this. Okay, it built just great. Now, one thing about a switch statement, and I hope you noticed that when I showed the switch statement earlier, a switch statement also has a default value. Now, the default is going to occur at this loop right here. So if the loop, if RCX is 0, the loop is not going to jump back up here. It's going to go to the next line of code. And the next line of code is basically this end case loop label. So the default would go right here. So what I'm going to do is I'm going to, I don't know, I'm going to push invalid menu, and then I'm going to call print string and call print NL. So that's my default case. Now I haven't defined this invalid menu, so I'm going to come up here and just create a new string. Okay, so it'll just print that string. And that's it. That is a table-driven selection case table processing loop. And if you notice, there's literally only one compare in all of this code. And think about all the compares you would have to have if you had 50 possible values that you're either analyzing data or, you know, think about the states, the United States, the states in the United States, there's 50 of them. Do you want to have 50 compares and 50 different jumps? Yuck, that code's going to get horrible. So instead of doing that, you can create a case table that has all of the data you're looking for, what functions should be executed if that's the data that you find, and then you have this simple little loop that actually goes through and processes everything. Now this is actually pretty important because I've asked this question on job interviews where I've asked candidates, describe to me what a table-driven selection is in either just general logic, computer science design, flowchart, or in assembler language, whichever you like. And there's a lot of people that don't get this one. So it's a simple logical construct that allows you to do a lot of stuff without actually having to have a lot of if statements. So, okay, so with that code over here on the right, I'm going to go ahead and open up a terminal. And I'm going to run it. Okay, well, it didn't really do anything because, I mean, it ran, but we would have to debug the thing. And I love to debug, but let's make this a little bit more interesting. I'm going to create a bunch of strings here. So I'm going to say function1 prompt defined by use selected option number 1. And I'm going to create 4 of these. Oops. So F3 prompt, and let me copy that. And then in each function, I'm going to do something. So in function 1, I'll have a no-op, and I'm going to say push function 1 prompt, call print string, call print and L, and then no-op. Now I'm going to just copy all of this. Oops. And just change the prompt that I'm going to be printing. There we go. Now you can call this anything you want. I don't know where I came up with prompt, but it's just something, maybe it's something from long ago. All right. And now exit function, yeah, let's go ahead and create another string called you've decided to leave the program. So I'm going to call this just exit prompt. I'm just going to say you've decided to leave the program. And we'll go ahead and just print that if the user types an X. Now we're not going to have the user type the X here, but we could. But instead, we're just going to go ahead and change the value inside of the program and build it each time. Okay, I forgot to put the L at my print L, and I believe it's a capital P, right? So to keep this simple, copy and paste, the best invention since sliced bread. All right, let's see how that works. All right, looks good. Now let's double check our, okay, we already did the invalid menu. Okay, so let's go ahead and test this now. We put in the number 1. Let's run it. Look at that, you selected option 1. Okay, I'm going to change this to the number 2. And I really would test every one of these. Well, that's number 2. What did I do wrong here? Did I build it? I don't think I built it. There we go, I didn't build it. There's number 2. There's number 3. I'm laughing because the first time I code something, it doesn't ever work perfectly, and this is working great. All right, so let's put the letter X, because that is going to be our exit option. You've decided to leave the program. And now let's put an invalid value. I'm going to put 9. And let's make sure our default works. Yep, invalid menu option selected. Wow, that was cool, right? Now, I would suggest you go through and debug this thing and just watch how this loop processes, and it goes through every value in the case table one at a time, interrogates the value, and then makes the appropriate decision on what to do. Now, the other thing you could do is you could put all of this into a loop. So you would have to make this into a loop. So I could say something like, I don't know, entry loop. And then right here, I would have the user. And I believe it's read text in the Komanetsky functions. So you could have the user type something in on the keyboard and place it into a buffer. Take a look at the read text function. I believe that's what I did. Yeah, read text. And you can see how to work that. And then down here, you would simply say loop. Or you wouldn't say loop, you would say jump entry loop. And then if the user typed an X, maybe you might do something like before you go to the next value here, you might want to do something like compare AL comma X, jump if equals to end entry loop. And then down here you could have end entry loop right there. So that I pretty much did the code for you there except for the text input. So really debug this, take a look at how it works, get the feel, watch it jumping around, you'll really get a lot out of it. All right, so that's our video on table-driven selection, switch statements inside of an assembler language program. I hope you enjoyed it. Debug it, play with it, add some more options to your case table. Actually put all of that into that loop where the user can enter stuff. Great project to do that. I hope to see you at our next video.